I was recently gifted this power supply to take a look at in a video. This is that video, so let's take a look at it. Something immediately intriguing about this power supply is that it's made by Intel, who probably aren't the first company that comes to mind when you think of power supplies. That's because this is most likely a reference design, intended to be copied by the usual power supply manufacturers, to give them an idea of what they need to make for a specific computery architecture. In this case, that's clearly not the kind of computer you or I would be using, but something more data center oriented, maybe even AI. We can see at the front of the power supply these huge gold contacts, which clearly indicate there's going to be a lot of current coming out. This power supply has an output voltage of 12 volts, which is very typical for computery stuff, although is slowly being phased out in favour of 48 volts, especially in high power systems like these. And the reason for that is that to get 3000 watts out of this power supply at 12 volts, these contacts, and all of the traces in the motherboard and wiring and things like that, have to carry 250 amps, which is insane. Quadrupling the voltage to 48 volts reduces that current requirement by 4 times to a much more manageable 60-ish amps. But that's less exciting. We all came here for the big numbers, and 250 amps is quite a big number. To try and better illustrate the performance and power density of this power supply, here it is next to two that we've looked at in past videos. These power supplies also have output voltages of 12 volts, and they're both between 40 and 50 watts, giving this old one a power density of about 350 watts per litre, while the much newer, nicer and more expensive GaN power supply has a power density of about 800 watts per litre. The Intel power supply has a power density of 2500 watts per litre, over 3 times that of even the modern GaN supply. Now, part of that incredible power density is just due to economy of scale. It's easier to make power supplies with higher power densities at higher powers. But a decent part of it is also due to, hopefully, good engineering, which we'll find out shortly. Of course, a power supply has to be quite efficient to cram that much power into such a small volume, and we can tell that this has decent efficiency because it has this sticker, 80 plus platinum, which basically tells us that above 20% load, the efficiency is at least 90%. So that means that at full power we can expect this power supply to have internal losses of about 300 watts, which would typically require a beefy fan and a load of heat sinks to get that power out and stop things getting too hot. However, this power supply is quite special. If we look at its bum, we can see it's solid, so it's got nowhere for the hot exhaust to come out, and that's because there isn't any hot exhaust air. Because as you can tell from the title of this video, this power supply is water cooled. Ooh. These funky looking conical things just above the output terminals are dry break disconnects, a special type of fluid coupling that allows connections to be made or removed without having to drain the coolant, because they have automatic spring-loaded seals inside that prevent any coolant from leaking. These are normally quite pricey because of their mechanical complexity, and I'm hopeful that that's a sign of quality to come. Now, it would be quite cool to power this up and do some experiments, but without coolant flow, the power supply would likely overheat even at quite low power. And I don't know about you, but I'm already kind of bored, so let's open it up. Now, the first vaguely interesting thing to note is that these screws aren't Posi-Drive or Torx, they're Phillips, so that gives a bit of a hint at who's designed this. Of course, another reason to not power this up prior to opening is that the internal capacitors are nice and discharged at the moment because this hasn't been powered up for months, if not years. Right, I think that's every screw out. Let's see if we can do anything. Aha! Oh, it's like an Apple product. So much black. There we go. This looks a bit like a piece of ducting that you'd typically see in an air-cooled server or power supply. But of course this isn't air-cooled, so I guess it's just insulation. This is really nice. We still can't see a huge amount. It looks like there's some controller-y, gate-drivey stuff going on up here. There's an intriguing chain of diodes here, so presumably some kind of snubber or protection network. I can see the pins of some 4-pin TO247 devices here, which is nice to see. I'm really hoping for some silicon carbide in here. This looks quite controller-y down here, this board. The fact it's sort of isolated from everything else. There's small, low current connections, and clearly some isolation between whatever's going on here and whatever's going on here. If we flip it around, we can see on the other side some evidence of some tight packaging. These are little breakout boards that they've basically made as right angle adapters for some big caps. Hopefully we'll get a better view shortly. But that's quite interesting because traditionally, if you want to mount a big through-hole electrolytic cap horizontally, you just bend the leads and solder them in. So I wonder why they haven't done that. Because these boards are certainly going to cost more than bending some metal. Ooh. Now here's a little sort of status LED. Now this is a bicolour LED. I'm going to guess green for good, red for bad, orange for something in between. But removing that rear panel has given us a bit more of a view of what we might need to remove next. Now there's quite a few connections between these two boards, which makes sense. I do hope these caps are actually discharged, otherwise you guys will never get to see this video. We can see a little bit more now. There's some very nice shiny metal thing in there, which I'm going to guess is the cold plate the water's flowing through. And this packaging is tight. Of course, packaging is usually pretty tight for server power supplies, but with no need to worry about a path for airflow, this can basically just be a solid block of power electronics. Beautiful. Well, we've found where this connector went. It was the LED. Now we have a decent amount of movement at the input end of this top board. Oh. 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 Ha 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 ha! What's going on over here? Something seems to be stuck. Nope. OMG. Wow. That's fantastic. So here's the two halves. Interestingly, the only beefy high current connection between them was this wire. Upon further inspection, we can see that the chunky brown wire is used for the positive connection between the boards, while the negative uses 6 paralleled pins of the multi-pin connector. In terms of isolation and clearance, this makes sense, as all the control signals between the boards will be referenced to that DC-, and assuming a DC voltage of 400 volts, that gives a maximum current of 7.5 amps, so just over 1 amp per pin, which again seems fine. This floppy stuff is all thermal interface material, just like thermal paste, but in a pad. Oh no, it's all gone in between the windings. Now the amount of thermal pad that's on all these various different components highlights a difficulty with designing something that's water-cooled. You might think that it's much easier because you just put all the heat into the water and takes it away to be someone else's problem. But if you're designing one of these and you've got a big fan, that's going to be cooling every single component. So a lot of the components, like the gate drivers, capacitors, that don't generate a huge amount of heat, you don't really have to worry about at all, as long as they have a bit of airflow. But if you're water cooling like this and there's no airflow, the ambient temperature inside the power supply is going to get pretty toasty. And you have to start worrying about cooling even little components that you wouldn't normally think about, just because there's effectively zero airflow. I'm going to keep a few of the intact bits to play with, and the rest of it will go in the bin. Right, well I just spent the last 40 minutes painstakingly picking out the thermal compound from the inductor windings, and I had the radio on, and there was a song that talked about brushing teeth, and I thought, well, that would be a lot easier. So in case you ever find yourself removing thermal compound from inductor windings, use a toothbrush. Right, so I've finally got this board decently cleaned up. I've also done a little bit of investigating. As suspected, this is the power factor correction board, which I was able to deduce from these labels that say PFC out and PFC out 2. From the presence of those two labels and 2 inductors and these 2 identical modules, it seems pretty likely that this is using an interleaved PFC circuit, but we'll dig a little deeper into the topology later. Unfortunately, upon further inspection, the TO247 devices hiding in here aren't silicon carbide, but that disappointment is made up for and more with what's hiding down this gap inside these modules. Googling the LMG3422 does reveal 600 volt 30 milliohm GaN FETs with integrated driver and other protection stuff. So these modules are quite exciting. Let's see if we can have any luck desoldering one. Now, as I alluded to previously, I think this could be quite challenging to desolder, particularly this pin which goes straight through to the heatsink, but I'll give it a go with the limited equipment and ability that I have. Whoa. I think these pads are probably going to be quite challenging too, just because it's an aluminium core PCB, so we're going to get a similar heat wicking effect with all the power from the soldering iron getting sucked away. I think this may have to be something I do off camera. Right, well, I managed to desolder one of these modules eventually. Here it is. Quite nice. Now, I'll leave the full analysis for future me, but we can see this is a pretty simple module. We've got the two GaN switching devices forming a half bridge, and the local decoupling capacitance for the commutation loop is up here. There appears to be some kind of isolation with these two transformers, presumably for power supply to the gate drivers. And when it comes to the construction, we can see it is indeed an aluminium core PCB, mounted onto a large metal block, which looks a bit like a heatsink, but as mentioned earlier, with water cooling the design requirements are quite different. Rather than making this a shape optimised for surface area to get as much heat into the air as possible, the best thing to do in this case is to just make it a solid block, so that we get as much heat transfer as possible from the face with the circuit board on, up to the top, which is where the thermal pad was providing an interface between this and the cold plate. The inductors have these little wires that go down into the PCB, which are then connected to the mounting holes, which are grounded. You can just about see through the tape that there's a darker patch in the middle, and if we take a look at the common mode choke over here, it's much more obvious what's going on. You can see here this copper tape wrapped around the inductor. This is called a flux band, and it's here to capture and absorb any magnetic fields that escape from the core. By grounding the flux band, we get a similar effect for the electric field. So a grounded flux band like this reduces both electric and magnetic field radiation into the environment. Something odd I've just noticed is that on the 4-pin TO247 devices, the power source and Kelvin source seem to have been joined together, which goes against the advice of all the manufacturers of these devices, and seemingly eliminates the benefits of having a 4-pin device with that separate Kelvin source. So I'm not quite sure what's going on there. Now let's return to the output side of the power supply, where I suspect we're going to see some even more exciting things. We still haven't found a transformer yet for isolation, so that must be here somewhere. And also, this is the part where we've got 250 amps flowing, so I'm hoping we're going to have some either very heavyweight PCBs or maybe even some bus bars. Yay! Well, let's flip it over, see what we can see. Right, well, all this solder's probably looking quite familiar to anyone who's opened a PC power supply. Let's have a little look around. I wonder if this will come off the controller now. Yeah. So that gives us a much better look at the controller board. I can see a microchip something here. Hopefully it's a PIC. Ah! It's a PIC! Lovely. Again, we'll look at this in more detail later. I thought this power supply might have been completely unused, but a little dead animal just fell out, which suggests to me that it has seen some use at some point. If we take a look at the other side, we can see a ton of output caps. Unsurprisingly, these are polymer to handle such high current. I can see some SiC devices in there. So this power supply contains both types of wide bandgap device. That's very exciting. Nice Rubicon caps on the primary side. And there's a few standoffs that connect the board to the cold plate, so let's undo those and see if we can get it off. If we're lucky, that's it. You do often get quite a lot of adhesion from these thermal pads, even though they're not designed to be sticky, usually. Yay! Ooh, this is exciting. Now that it's completely free, this cold plate looks like it belongs on a gamer's graphics card. It's quite nice. But even more nice is what's been revealed beneath. Wow. There is a lot going on this board, but it's quite mucky with all this thermal compound. Plus, my SD card's nearly full, so I'm going to spend my evening cleaning this up and doing a bit of reverse engineering, and I will return in the morning. Right, here's the board nice and clean. We can see a lovely fat wire inductor here, as well as a lot of metal and a few little strange packages that look like something you'd expect to come in the post. I've spent a few hours following traces and buzzing out connections on both of these boards, and have managed to put together a full schematic for the power section of the power supply. Now, in this schematic I've included all the major components, and I've added a few component values where I could read them, which is basically just the big caps. Now, this is a bit overwhelming just having everything all at once. If you want a bit of a challenge, feel free to pause the video now and try and work out yourself what's going on. But for the rest of us, let's start breaking this schematic down, and the easiest place to start is by splitting it in half, into the circuits that are on these two boards. As always, we're going to follow the same path as the electricity, which means starting on the input board. The mains enters the power supply through this beefy input connector, which has an earth wire coming out the back to ground the chassis, while live and neutral are passed through this small ferrite toroid, which acts as the very first step of input filtering, and that I've represented on the schematic with a common mode choke. Once power gets onto the board, the first things we see are, as always, input protection and input filtering. Inside this yellow heat shrink is a fuse, and this big green thing is a MOV or metal oxide varistor, which will clamp any excessive voltage spikes on the mains. Following that, we have two class X capacitors bridging between live and neutral to filter out high frequency noise. On the back side of the PCB, underneath these capacitors, is a chain of 3 series resistors, again between live and neutral. These are to discharge those filter capacitors so that they can't give you a shock when you unplug the power supply. Back on the top side again, we can see a pair of Y caps connecting both live and neutral to earth, again for further filtering. The next thing after the Y caps is this chunky common mode choke, which is actually bigger than the PFC inductors we're going to look at shortly. On the back side of the PCB, underneath the common mode choke, and in parallel with its windings, are these white components that look a bit like multi-layer ceramic capacitors. But having capacitors in parallel with the common mode choke would create a path for high frequency noise to bypass the choke, and would make it pretty much pointless. So these aren't actually caps. The designator SA, combined with their white appearance, tells us that these are actually surge arresters, also known as gas discharge tubes or GDTs. These are designed to provide a safe path for very high voltages to jump across, and they're filled with special gas so that any sparking or arcing internally doesn't cause permanent damage. Just as a backup in case something goes wrong, you can see these little spiky solder bits. These are spark gaps, which essentially serve the same purpose, but without the special gas and nice ceramic package. After the common mode choke, the neutral flows through this resistor for current sensing. You can see the 2 Kelvin connections for it running down along here. And after that, it then passes through this relay, which is used to turn on and off the main section of the power supply when the right connections are made on the smaller pins of the output interface. And after that relay, there's one more X capacitor joining live and neutral once again. That's all the boring bits of the input, so let's strip all that crap away from the schematic and see what we're left with. So what is this circuit? Well, it's an interleaved totem-pole power factor correction circuit, which is nice because it combines multiple things we've looked at in the past. As a quick reminder, active power factor correction is the use of fast switching transistors to control the input current and force it to match the input voltage waveform. Most active PFC circuits are based around the boost converter, which brings a number of additional benefits, including simplifying design for a wide input voltage range and reducing the amount of bulk capacitance required. In the past, we've looked at the simplest form of active power factor correction, which is simply a standard full-bridge rectifier followed by a boost converter. While this may suffice for simpler, lower performance power supplies, this beast deserves better, which is why it was given not 1 but 2 totem-pole PFC circuits. These are the same fundamental circuit as the simple boost PFC, but rearranged to eliminate all the lossy diodes, swapping 2 for the fast-switching half-bridge of the boost converter, and the remaining pair for a simple low-frequency active rectifier. The interleaved part of the name just means that the 2 boost converters operate out of phase, doubling the effective switching frequency and reducing current ripples significantly, just like an interleaved or multi-phase buck converter, which we've also looked at previously. The current drawn from the mains needs to be accurately measured so that the PFC circuit knows what it's doing. That's the job of this high bandwidth current sensor, which is the final component current passes through before splitting off into the 2 inductors. Using this, the controller can ensure that the shape, amplitude and phase of the input current are all correct. It looks like this trace got a little bit too thin here for the designer's liking, so they added some solder to beef it up a bit. We're going to see a lot more of that on the other board. Now we've already had a bit of a look at these 2 inductors. We know that they have grounded flux bands for reducing electromagnetic emissions, and beyond that there's not an awful lot to say. They've got toroidal cores, which is pretty common for power factor correction. It's the best core shape for EMI because it hasn't got any sharp edges or splits in the core. But it has the problem that it's quite difficult and expensive to wind because the core doesn't split. So if you've got to wrap 20 meters of wire around it, you have to pass all 20 meters through the whole of the donut for every turn, which is why they're not more widespread. After passing through one of the inductors, the next thing the electricity will see is the GaN half-bridge modules, which are definitely the nicest part of this input board. Let's remove the one we desoldered earlier and take a closer look. So here's the GaN module, which is effectively just a half-bridge. There's the two GaN devices from TI, and a very small amount of DC capacitance, which is just there to keep the loop inductance low and prevent overshoots and voltage spikes when the transistors turn on and off, which could damage them. The reason the capacitors are at one end is because this board is using a fairly modern layout that typically you only see with wide bandgap devices, particularly GaN, which involves routing the path for the return current to the capacitors underneath the two transistors, which results in a much smaller commutation loop area than a more conventional and maybe intuitive design, placing the capacitors above or below the transistors. That does mean that this board must have multiple layers, at least two, and it's an aluminium core board, which can't be cheap, because typically aluminium core boards, like those used in LED lighting, have just a single layer. While these GaN devices do have integrated gate drivers, they do still require an isolated gate drive supply and signals, which is the reason these two small transformers are here, which, paired with these rectifier packages and a few other components, create two isolated power supplies for the gate drivers. These digital isolators at the top of the board isolate the gate drive signals to give both of these GaN packages fully isolated control signals. Looking at the two GaN half-bridge modules side by side, you can see how they're approximately mirror images of each other, but the fact they aren't identical would add quite a bit of cost, as this is two separate PCB designs, two separate assembly processes, and each board even has a slightly different set of components. You can see the board on top has 5 DC capacitors, whereas the one beneath can only fit 4. I suspect if this wasn't a reference design, and cost was more of a concern, a little more effort would have gone into laying out this bottom board so that these two GaN boards could be the same. Because I'm not really sure why it was necessary to have the two PCBs facing inwards like this, which is ultimately what's led to this requirement of two different PCBs. It seems like there wouldn't be any obvious issues with just replicating the same module in the same orientation. Anyway, after passing through the GaN half-bridge, the electricity is now DC, and its power factor has been corrected. Now all that's left is to shove it into some caps. As we saw previously, these are mounted onto these little breakout boards, and I'm not really sure why, because it just seems like unnecessary complexity and cost. It's not like there's any mechanical advantage over just bending the leads, though I suppose there is some additional rotational stiffness if this power supply were to be used in a very rapidly rotating server. In total, these two capacitors provide almost 1,000 microfarads of capacitance, which at 400 volts would be about 80 joules. Once again, I'm glad these aren't charged. Now you probably noticed this earlier, but hiding underneath these capacitors are a few chips. Starting with the least interesting one, over here is an op-amp, which is used for amplifying the voltage coming out of that current shunt we saw at the input. This next chip is a 6-channel digital isolator. I'm not sure what signals it's isolating, other than the fact they're digital, though if I had to guess, I'd assume at least some of these channels are used for PWM. And finally there's this QFP package, which is a Texas Instruments C2000 microcontroller. This is the real brain of the power supply, or at least this PFC section of it, as this will be taking in voltage measurements and current measurements, and doing lots of clever calculations very quickly to work out what switches need to be on and which switches need to be off, to keep the input current sinusoidal and in phase with the mains, and also to regulate the voltage on the main DC link capacitors. The fact there's such a beefy microcontroller in a power supply really does show the leap in complexity from the simple flyback topologies we've looked at in the past, which can get away with simple peak current mode controllers and a few passives. That's the end of the electricity's journey through this board, and it now passes through this beefy terminal and this multi-pin connector over to the other board. Now, just as we could describe the other board as a fancy rectifier, this board is just a DC to DC converter, with a 400 volt input and a 12 volt output. Once again, this schematic may at first appear a little overwhelming, but we can very quickly shrink it down by combining all the paralleled components. One good thing is that this board has far less boring filtering and protection, and almost everything on it is exciting. The topology used for this DC to DC converter is the phase-shifted full bridge, which is pretty common in higher power applications like this, and is very different to the flyback topology we've looked at in the past. There are quite a few things going on here, so let's begin with the full bridge and what's meant by phase shift. A full bridge consists of two half bridges made up of a total of 4 MOSFETs. The output of each half bridge can be either positive or negative. If we switch both in phase with each other, the voltage between the two outputs is always 0. If we delay the switching of one of the half bridges, introducing some phase shift, we get a short period where a voltage is present between the outputs, alternating between positive and negative for the rising and falling edges respectively. The primary winding of the transformer is connected between the two outputs, so sees these alternating voltage pulses, which therefore appear on the secondary winding with a magnitude given by the input voltage divided by the turns ratio. This transformer has a center-tapped secondary winding, which is used to simplify the rectifier, needing only 2 diodes rather than the 4 of a full bridge. In this case, synchronous rectifiers are used, which are also easier to implement with a split secondary. This gives us a pulsed DC output, which we can't connect directly to the output capacitors, as there would be huge current pulses whenever the voltage appears and the capacitors are instantly charged up. For this reason, we need to add an inductor in series with the output to smooth that current into the capacitors, just like a buck converter. We can actually consider the output stage of a phase-shifted full bridge as a buck converter, with the width of the pulse, or the duty cycle, controlled by the phase shift between the 2 primary side half bridges. There's one final component of a PSFB that I conveniently left out until now, because it just makes things a bit more confusing, and that's an inductor in series with the primary winding of the transformer. This has a few effects on the converter, most of which we're going to ignore today, but the most important is that it enables soft switching. This is because when current flows through the primary winding, it also has to flow through this inductor, which then stores some energy in its magnetic field. When the switches in the full bridge turn off, the energy in this inductor forces current to continue circulating, which charges or discharges the output capacitance of the MOSFETs until the voltage of the switching nodes between the devices is clamped by their body diodes. At this point, the opposite switch turns on, and because current is already flowing through its body diode, the voltage it has to switch is pretty much 0. As power is voltage times current, one of those being 0 means no power is dissipated while the MOSFET switches, so there's no switching loss, at least in theory. This is called the zero voltage switching, or ZVS, and I have a video specifically on the topic coming soon. Power first comes onto the board through a beefy terminal and a multi-pin connector, matching those on the output of the first board. It's then immediately fed into 3 large capacitors, which might seem a bit pointless because it's just come out of 2 even bigger capacitors. But this is because both boards require local capacitance to regulate their voltage and prevent spikes. If this board relied on the capacitors on the other board, there'd be too much inductance in the connections between the boards, which would result in an unstable DC bus with voltage spikes that could destroy the devices. Following these capacitors is a full bridge consisting of 4 650-volt silicon carbide MOSFETs. I know quite a few of you have wanted to see something with silicon carbide MOSFETs in, so here you go. The fact that these MOSFETs are switching several orders of magnitude faster than those on the PFC board meant I was even more surprised to see they have their source pins joined together on the PCB. At such high frequencies, this seems like a very bad idea. And while the soft switching does reduce the rate at which the current through the MOSFET changes, which lessens the impact of the shared current path, I just can't think of any justification for this decision, as the internal connection of the Kelvin source pin is so weak, they might as well have just left it disconnected. And why bother with the 4-pin package if you're just going to use it as a 3-pin one? If anyone knows of an actual reason to do this, please leave a comment below. One of the outputs of the full bridge then passes through this strange white box, inside which is an inductor. This inductor is in series with the primary winding of the transformer, the other end of which is connected to the second output of the full bridge. Coming out of the PCB next to the inductor are these 2 wires, which are the 2 ends of the transformer's primary winding. Now, these aren't any old wire, these are Litz wire, which means they're made up of many individually insulated strands twisted together in a special way, to eliminate as much as possible the impact of both skin effect and proximity effect. Litz wire is very common in high-frequency magnetics like this, but once again, it's not the cheapest thing in the world, so high-volume manufacturers are often keen to find lower-cost alternatives. When it comes to the transformer itself, it's quite tricky to see what's going on, it kind of just looks like a block of metal. There's clearly a ferrite core, though its actual shape is quite hard to make out, and these significant lumps of metal on top are presumably here for thermals, to draw as much heat out of the core and the windings as possible, to pass on to the cold plate that was sat above. There's no obvious secondary winding of the transformer, but the output connections aren't made with wires or pins onto a PCB, but rather through all of this chunky metal, which really highlights just how much current is passing through. The transformer features a split secondary design, as you can see on the schematic, with the two ends of the transformer joined to the PCB here, and the midpoint up here. The inductor that's in series with the midpoint is the chunky flat wire inductor we saw earlier, and that's mounted to the PCB here and connected to the transformer midpoint. If you look very closely in this gap, you might be able to see some gold and some green. That's because sandwiched between these bus bars is another aluminium core PCB. Mounted onto this PCB are some MOSFETs, which form one of the two synchronous rectifiers, used like diodes to rectify the output of the transformer. As I mentioned earlier, the use of MOSFETs to replace diodes is a common trend in applications looking for higher efficiency, and because diodes have a fixed voltage drop, their negative impact on efficiency gets worse and worse the higher current you run at. This power supply is outputting up to 250 amps, which would result in several hundred watts of loss if it were to pass through a standard silicon diode or even a Schottky diode. For this reason, synchronous rectifiers are a must. Unfortunately, we don't really have any nice way to see them, because they're sandwiched between the transformer and the bus bars, which are both soldered into the PCB, and have far too much thermal mass for me to be able to desolder them. But we can tell they're here, not only because of the PCBs, or the SR1, SR2 designators on the silkscreen, but also because both of these PCBs have a single, small additional connection, which is subsequently routed off to some resistors, capacitors and diodes, a clear indication that this is a gate terminal, and these passives form the gate drive circuit. After passing through the synchronous rectifiers, our high-frequency AC in the transformer has once again been returned to DC, which means it's time for some more capacitors. As we have a very high current and a fairly low voltage, there's only one natural choice for this, which is of course polymer capacitors, of which there's a surprisingly small amount. Though with a rating of just 16 volts, these are able to cram a lot of capacitance into quite a small volume, with a total output capacitance of 9,000 microfarads, which at 12 volts will store about half a joule. Taking another look at the output inductor, we can see these windings are really fat, they look like coins, and despite their immense cross-sectional area, the whole inductor was completely stuffed with thermal compound, clearly to try and suck out as much heat as possible to pass on to the cold plate above. That's probably part of the reason why the windings have gaps between them, just to spread out those losses and give them more chance to escape. These little gaps will also help reduce proximity effect between windings, which results in increasingly higher losses in each turn of the inductor, as they all induce eddy currents into each other. A bigger gap between windings gives the magnetic field a little bit more time to disperse before intersecting with the next conductor. The core material is quite interesting too, presumably some kind of ferrite, but I'm a big fan of this yellow coating. If anyone knows what the yellow means, make sure to leave a comment below. The final thing the current passes through before leaving the power supply and going on to be used to produce an AI cap video is these 4 parallel resistors, followed by these 4 parallel MOSFETs. Together, and combined with a chip hiding on the other side of the board, these form the reverse polarity protection, stopping current from flowing back into the power supply. This is yet another case where, due to the really high currents, a simple diode won't suffice, and so instead we use something called an ideal diode, which is basically a MOSFET paired with a clever controller, which turns it on if any current starts flowing between the source and the drain, and very quickly turns it off if it starts flowing in the other direction. Initially I assumed these resistors were part of the ideal diode circuit, as many ideal diode controllers require a shunt to measure the direction of the current. However, the ideal diode controller on the other side of the board doesn't require resistors, and is smart enough to do everything with just drain source voltage measurement. That doesn't mean these resistors aren't used for current measurement though, and they're most likely connected to the controller of the power supply, so that it can monitor how much current and power is being drawn. Now you might be wondering what these bits are next to the transformer that we haven't looked at yet. These 3 components actually form a second mini power supply inside the big power supply, which is used to produce the standby output for powering bits of the server that need to be on all the time, like fancy network adapters that can be used to remotely power on the server. We can see from the label that this auxiliary power supply can deliver up to 36 watts, which is pretty decent and not far off the power of the power supplies we've looked at in the past. Just like those power supplies, this uses a flyback topology, with the primary side switch underneath this big block, the transformer or coupled inductor in this white package, and the rectifier diode underneath this metal block. This flyback converter uses an interesting integrated controller in a 7-pin DIP package, which contains both the primary side switch and associated gate driving and control circuit, allowing the design and general layout of this sub-converter to be much simpler. Speaking of control, I've done a little bit of reverse engineering on that side of things too. The power supply contains two microcontrollers, the PIC24 and the C2000. The PIC is like a frail old man, and the C2000 is like his young, fit son, much faster and stronger, but still subservient to his father's demands. The language they speak when talking to each other is SPI, and for safety, all of their conversations pass through this digital isolator. The C2000 is in full control of the power factor correction board, with its PWM outputs going directly into the digital isolators feeding the GaN devices, as well as to the gate driver controlling the slow switching half bridge. On the main control board we can find a dedicated phase shift PWM controller, which is handling the control of the phase shifted full bridge. It has 4 PWM outputs which pass through the same digital isolator as the SPI communications between the microcontrollers, and these then go on to directly control the 4 MOSFETs of the full bridge. Crossing this isolation boundary we can also see 4 analog optocouplers, used to provide the controller with analog feedback of the output voltages of both the phase-shifted full bridge and the PFC. The PIC is also connected to a few of the small pins on the output connector, presumably for some kind of control or monitoring interface. Now earlier on I mentioned this curious chain of diodes, and predicted they were some sort of snubber or protection circuit. That was wrong. These diodes are used for simple passive rectification at startup, and probably also when only the standby power supply is being used, as at such low power, the losses of running the PFC circuit probably outweigh the gains. One thing I'm not sure about is why there's a need for so many diodes, and why they're in this configuration of effectively 2 full bridges. I've tried with the multimeter to buzz out every possible connection to anything on this board, and I just can't find anything else apart from neutral and DC plus and minus that these diodes are connected to. So if you recognise this configuration and have an idea what it might be doing, let us all know in the comments. So that's it for this video. It was mostly unscripted. Let me know your thoughts on that, whether you prefer it or find the pauses and repetition and less concise explanations a bit irritating. And also let me know what you think about the lighting. I've been messing around with that a bit recently. But anyway, thank you very much for watching. Until next time, bye!